lines of what my PhD research was really based on, which was material science. And it really opened a whole new world up to me when I moved from atmospheric science, which was my background up to that point, to material science of how I view the snowpack and how I view just ice in general, for that matter. So I'm going to try and share that with you today and kind of give you the outline of my experience, more or less, and where it's brought me today. Before I do that, I'd like to talk to you about Japan to start out, actually. So, yeah, so let's toss this in there. So I just recently got back from my first trip to Japan. Has anyone been to Japan or been skiing over there in here? A couple, one maybe? All right, well, you guys should all go. It's awesome. And I wasn't even there for powder season. You know, I just missed powder season. But I got this grant through Montana State University, a faculty excellence grant, to go over and kind of meet and greet with the snow science researchers over there, tour their facilities, kind of build what I hope is going to be a collaborative relationship for future work. And I had a phenomenal time. The first place I went to was the Snow and Ice Research Center and visited their cryospheric environment simulator in Japan. Just to give you to orient you a little bit, this is Tokyo right here. So I spent all my time just on this Honshu island. And after that, I went to Nikaya, the Nikaya Museum of Snow and Ice. I'll talk about each of these a little bit more. In Kaga City, Japan. Then went to Nozawa Onsen Ski Resort. So I did do a little bit of skiing there, but it was, instead of calling it Japao, we called it just slush because we just missed the window of powder skiing there. Then went to the Forestry Research Institute, Tokamichi, and the Snow Avalanche and Landside Research Center in Miyoko. And I learned a lot there. One of the things that I took away from that trip the most was just the history that they have working and researching snow in that country is phenomenal. I mean, they get a ton of snow there. It's one of the snowiest places in the world. And they're inundated with it in their community and their ski hills. And it's something they've had to deal with, and figure out and study, so they have. So I'll just go quickly show you each one of these places. Cryospheric Environmental Simulator. This is like James Bond in real life. This is a huge garage size, kind of hangar size room that they have to play in. They make it snow from the ceiling. They collect it on this 5 by 3 meter table. They can then tip the table and, make weak layers and blow wind on it, do all this sort of stuff. So they make, kind of to scale size snow slabs, which is pretty cool. And they also have this circular wind tunnel. So this is looking in the wind tunnel, lining it with snow, putting down a little snowpack, and that's a circulating wind tunnel. So they're able to get some high wind speeds and have really good laminar flow in there for snow and wind studies. So pretty cool place. That was fun. That was in Shinjo. Oh yeah, I learned 3 Japanese characters. I'll share them with you, and maybe you'll have these down too. This is the Japanese character for snow, or yuki as they say. So if you're looking for a tattoo, I don't know, this maybe be a good one. I like it. So that was the Snow and Ice Research Center. Then the Nikaya Museum of Snow and Ice. You might recognize the name Nikaya if you've ever seen this in a paper or a book or a presentation or something. He's the one back in the 20s and 30s kind of figured out what the temperature and supersaturation needed in a cloud to get different types of ice crystals to grow, which I thought was, we all think is pretty cool. But the fact that he was doing it that long ago just makes it that much better. He has an entire museum dedicated to him in Japan, which I thought was really impressive. Nozawa Onsen Ski Resort. This is what we were saying at that wet slide that we were looking at today. They need something like this behind those houses, right? Yeah. So, anyways, this Nozawa Onsen Ski Resort. There's good terrain out of bounds, of course, in all directions. But I really love the way that they manage their terrain there. These red areas are all trees. They're all just closed. They don't want to patrol it. They don't want to deal with it. Just close all that terrain, so everyone's just supposed to stick to the slopes. I mean, it's enter at your own risk. Each resort is different, but to ski out of bounds, you're supposed to file an actual backcountry ski plan with the ski patrol there, like trip leader, gear, number of people, where you're going, what gear do you have, like all this sort of stuff. It's supposed to be what you do to ski out of bounds there, and then it's, you're off on your own risk. And this is just an example of, they don't do much explosives work there, but they like to build lots of structures to catch and prevent avalanches. So this is a particularly large one that we came across there that I think is supposed to catch big wet slides in the spring. Then went to the Snow Avalanche and Landslide Research Center. Again, these are 6 meter tall snow fences just kind of randomly all over the place as you drive up through the mountains there. It's a very mountainous country. And so they just, they don't do control work. They just kind of prevent avalanches altogether. And one of the things I learned there that is pretty interesting is that here's a table that one of them showed me where if you look at the Columbia Mountains, Canada, Alps, Switzerland, 82% of the weak layers, causes of weak layers are these persistent weak layers like we have here also, depth ore, faceted crystal, surface ore, and so on. They don't really deal with that over there so much. I mean, they're more looking at, just by the numbers, they see more storm snow kind of instabilities at interfaces. So they're actually trying to correlate that back to, not just is it Graupel or is it a dendritic snowflake, but how much rime, like where on the spectrum is it, and how does that relate to their occurrence of avalanches? So not something I'd really thought about before, but, this not just a regional difference, but kind of different areas around the globe have different things they worry about. So what we think about is not something they think about so much, which was kind of eye-opening. This Forestry Research Institute was probably one of the most impressive places to go to just because of its historical context. This is actually a tunnel built under the ground that you see here that goes out to this slope. There's a big steep slope here with trees on it. And 80 years ago, they built this tunnel so that they could go out to this slope, plant different trees in the hillside, and then stick a little pole thing of some sort out there and measure glide and measure sort of just general creep of the snow slope down the hill. 80 years ago they're doing this, right? Which is super cool. And up to 100 years ago they've been digging snow pits and documenting their snowpacks at this site. So these poles right here actually show the max snow depth going back 100 years. There's 100 poles here that are planted out in front of that. And what that looks like plotted is this. So this is snow depth and time on the x-axis, and this is going back to 1917, 1918, all the way through the present year. So there's 100 years of snow pit data. So one heck of a data set, right? Which I thought was pretty cool that they just sort of tossed this piece of paper to me as we were walking out of the place. Like, by the way, this is what we do here. We have 100 years of data that we're playing with all the time. So that was a eye-opening experience. Also, it wouldn't be a trip to Japan without lots of sake and sushi and other random creatures from the sea. These are my other two characters. All right, so this is Jun Mai. All right, Jun Mai is pure rice and water sake, so it hasn't been cut with any other sugars or any other distillate alcohols or anything like that. So you want to learn how to just go straight for Jun Mai when you walk into a restaurant. I basically learned how to say konnichiwa, Junmai, arigato, which is thank you. So hello, your best sake, thank you. Okay, that was it. That was Japan. And it wouldn't have been a complete trip without dressing up like a samurai along the way. Okay, so that was Japan. Sorry, I just had to toss that in there because I'm still pretty stoked about it. And I want everyone to go. And when you guys go to ISSW and see the Japanese cohort walking around, they're such nice, hospitable people. Just walk up and introduce yourself. And they talk way better English than they know. So it'll be fine. There'll be not much of a language barrier. All right, so back to my talk. Sorry for the long segue there. But I like to ask the question whenever I start these talks is what is snow? We usually think of, skiing, but we also think of snow as being, this white substance. It's cold and it's reflective. Would you guys all somewhat agree with that statement? Generally? Okay. So from the materials science standpoint, from the materials perspective, snow is not actually that cold. It's actually really hot, right? Because it's always near its melting point. So you could also think of snow as being this black, hot, absorptive material. So it could be, hot because it's near its melting point. It could be absorptive depending on the wavelength that you're looking at. At the wavelengths we see it's very reflective. But at like near infrared wavelengths, it can be more absorptive. So it just depends. So this is kind of the first little turn I took in my mind of looking at snow and ice much differently. Now applying this to what are we interested in our snowpacks for avalanches in particular is the interfaces, the stratigraphy that we get, right? So what causes that? All types of different winter precipitation. So we have snow, we can get sleet, we can get freeze rain, we can get rain, we get crusts, and I'm not even talking about wind yet, we get wind effect. And this causes all these different, you could think of it, types of snow to get put down, or what I like to think of it as is different types of materials that get put down. And each of these different materials are going to have different properties, right? So you could end up with more of a composite material, if you will. And then, of course, once the snowpack is down, once you have this stratigraphy set up, all sorts of stuff is happening to it. You've got solar radiation, you've got long wave radiation from the clouds in the atmosphere, you've got sensible heat losses to the ambient air, you've got latent heat flux from phase changes, you've got the ground heat flux, and there's tons of stuff happening. So the idea that it's cold and nothing's happening is definitely something that won't get you very far when you're thinking about how the snowpack's changing over time, because it's actually quite dynamic, and this is partly why. So this is a game I like to play. Maybe you guys have played this one before, but it's a game called Round or Facet. Ethan, you're not allowed to tell them the answers, okay? So, okay, round or facet. You guys can all chime in. Round or facet. Rounded grain. Thanks, Ethan. It's just typically associated with sintering, bonding, stability, absence of strong temperature gradients, and so on. How about this? It's a square, yeah. Or we might call it a facet. And it's associated with poor bonding structures, instability, presence of strong temperature gradients, and so on. Okay, now, smart guy. How about this?
Rounding facet.
Rounding facet?
Faceting round.
Or is it a faceting round? Yeah, that's the whole point. Yeah, what is it? So when you are digging your snow pit, looking at your snow grains, and you're trying to identify these things, how are you actually determining what's happening in this snapshot in time that you have, that you're digging the snow pit and looking at, you know? How would you kind of guide yourself to making a decision on one or the other, typically?
Temperature gradient.
Temperature gradient. Yeah, exactly. So this is what I was taught to do when I took my level 1. I don't know about you guys. Maybe I was level 2. I don't remember anymore. But anyways, you look at your temperature gradient, and if it's greater or less than 10 degrees C, then you're either in a rounding regime or a faceting regime, and there you go. That's all you need to know. So you might have taken your every 10 centimeter, or if you're really got time to spend out there because you're getting paid to do it, you might spend like every 5 centimeter temperature gradient out there, and then you say, oh, this is a rounding facet, it's a faceting round. So you might have a temperature thermometer that looks something like this, and that was kind of the whole point of this research that I'm talking about tonight is related to, is how much can you trust this? What is this really telling you? Or should you trust it at all, actually? So what we typically do is go out into the snowpack and we identify our different layers and we put our temperature probes in there. And I'm going to go ahead and just cut to the chase on this one and give you the conclusion of the study, which is when you're evaluating weak layers in a dry snowpack and you got your temperature gradient set up and your snow slabs and interfaces identified, I'm going to say that you should just leave your thermometers at home. Forget about it. Just forget about it, because I don't think it's telling you what you think that it's telling you or what I think it was telling me. And I know what you're thinking when I say that is like, wait a minute, seriously? Or you might be thinking this. Anyone? Anyone? I know there's some disapproving koalas out there. I'm telling you to leave your thermometers at home, but let me explain a little bit. All right. So as you guys all know, slab avalanche activity has been observed to occur near icy layers or crust facet combinations. This isn't a new thing. I'm not the first one to come along and say that or figure that out. People have been saying this for a long time. But the question has somewhat remained: why is that? Why do you get these facet layers that seem to form near crusts or icy layers that can sometimes, frankly, catch you off guard? What does that mean? How do they get there? How can we understand that and forecast that better? And the theory's always been that there must be, if it's faceting there must be a stronger temperature gradient, right? But you're not measuring it. And part of the reason you might not be measuring it is because those measurements with the thermometer are quite coarse. So like the diameter of the thermometer itself could be 2 millimeters. What if the temperature gradient is less than that? So I remember thinking if it's 10 C per meter, or 1 C per 10 centimeters, or 0.1 C per 1 centimeter, right? I mean, at what point does that continue to scale? So that was the question. And this, kind of got into my mind back during 2011. This was actually the year I worked at Sylvan Pass, and this Martin Luther King crust got put down, as it came to be known. This is from the Avalanche Review. And it was a very widespread over the western United States, kind of freezing rain crust that people had to deal with in different areas more than others, but everyone kind of had to deal with at least a little bit. Do you guys have it here? Do you want to remember? Maybe it wasn't that big of a deal here. It was sort of...
Through elevation.
Yeah, it was at the right place. So anyways, it was an ice crust that formed on the snow, and it would get loaded and then avalanche and then get loaded and then avalanche, and people in Utah really had a heck of a time with it, for sure. But anyways, the idea was to try and represent that in a laboratory setting and study it. That was the point. So let's just quickly draw. The best way to approach these things as a scientist is definitely with a cartoon, I think. So I like to have the cartoon always going. And so here you have our snowpack. We have our icelands that got put down, snow on top. And there's always going to be some temperature gradient because it's generally warmer at the bottom than it is at the top. And because of that, you get a water vapor concentration gradient. So that's what the little blue dots are. So you've set up this this scenario for heat flow to move from warm to cold, and for water vapor flow to move from areas of high concentration to lower concentration. So the question becomes, what happens right here at the interface? And I said before that, if you think of snow as different materials, each layer being a different material, then what is this layer of pure ice? I guess definitely a different material from the snow around it. So what happens is you get conduction through the individual snow grains. What happens when it makes its way to the solid piece of ice? Or what about conduction across the pore spaces in the snow? What happens when it makes its way to the ice? So just to give you kind of a rule of thumb, pure ice has a thermal conductivity of about an order of magnitude greater than snow. So there's a big discontinuity here at this interface. So you'd expect something to be going on there that maybe we could see in the laboratory. So to study that, we just made exactly the same setup in the lab. We have snow, and then an ice lens, and then snow. We put it in this tube with copper caps so we could put a temperature gradient on it. And then also, in a different setup, put little micro thermocouples that are 79 microns at the bead, above and below that ice lens, so we could see, is there a temperature gradient above and below there that we're not measuring with our big thermometers, but maybe we can measure them with these little tiny thermometers, right? So that was the idea. So from the micro CT work, we did a time-lapse micro CT. Micro CT is a CAT scanner for small things. We have it in our cold lab at Dartmouth, but also at MSU. We have all the same stuff. And what we saw was we started off with a nice smooth lens, ice lens, and we got this crystal growth that occurred from the bottom side of it while all the grains around were becoming faceted. And this was actually seen first in the literature by Ethan Green during his dissertation. He saw something similar to this with his experiments. So we saw that again. The question I had was, how smooth is the top surface of this ice lens? Because the idea is that it remains smooth and it's a nice sliding surface. So I looked at these samples with a scanning electron microscope. And what we saw was this is what the new ice crystal growth looked like below the ice lens, while the top of the ice lens did remain smooth. So these are grain boundaries on just a smooth piece of ice. And then, of course, we saw the faceted snow grain as well. So this snow grain was right above the ice. So it looks like we're getting that sort of setup that we were just talking about happens naturally, where you get this maybe bigger temperature gradient near the interface, and you get more faceting there. And from the micro CT, you can plot lots of stuff and get lots of numbers. There's not much to learn here besides this trend going up in the specific surface area is indicative of kinetic snow metamorphism, and going down for the new ice crystal growth is maybe stepwise lateral crystal growth. Just some things you can pull out of micro CT data. But the more interesting stuff that we looked at with, in the quantitative sense and plotted was the degree that this temperature gradient that we saw at the interface was greater than what was imposed. So in this plot is looking at, the blue line is what we imposed on the sample. So this is like 100 C per meter temperature gradient, which is pretty strong, but it takes time to do these things, so we want things to happen quickly. But in the red is what we measured. So what you see here is a much stronger temperature gradient right above and below, which I kind of blow up on the other side. And so even though we were only imposing a 100 C per meter temperature gradient, what we saw was about a 300 C per meter temperature gradient above and almost like a 600 Celsius degree per meter temperature gradient below. So like factor 3, factor 6 greater than what we were imposed, which is really high, right? And another way to look at that, which I think is kind of more intuitive, is not just how much greater is it, but how much greater is it as we turn down the temperature gradient more to the natural world. So here we looked at 100 C per meter, turned it down to 50 C per meter, down to 10 C per meter. This is kind of the magic number, right? 10 C per meter, and then down to 4 C per meter. And what we saw when you look at the temperature gradient, how much greater it becomes as you turn it down, was that even when we get to 10 C per meter or below, we were still seeing really large temperature gradients occurring at that interface. So this would be something you'd never be able to measure in the field, at least not with your standard equipment. but it was much greater. And it actually got to be, in terms of how many times greater, it got to be more so the lower the temperature gradient was. So this was like a 30 or 40 times greater than what was imposed at a 4 C per meter temperature gradient. So I'm kind of throwing out all these numbers at you, and I totally understand if you're getting lost in there, because I am too. So I'm going to tell you about kind of the way I like to think about this is what I call the temperature gradient multiplier. So you can think about what's your actual temperature gradient near an interface. So you're the one out in the field, you're digging the pit, you're taking your temperatures, and you come across an interface where there's an obvious crust or ice layer or something like that, and you want to know, well, what could this temperature gradient here be? What I'm trying to kind of build up as a library now, current research, is by what should you multiply the temperature gradient that you're measuring? So if you are measuring above and below or across that interface, a 10 C per meter temperature gradient or less or more or whatever, what should you think about that could be? And the data would show that even if you're less than 10 C per meter, if it's an ice-snow interface, you might want to multiply that by 30, which would take you into that kinetic snow metamorphism regime, which would then make it not that surprising when you get a weak layer there, a faceted weak layer there. So that's kind of the take-home from this, is that this temperature gradient multiplier, I hope we'll continue to expand that data set and build on that more. But that's a general idea. We have some micro CT imagery here. And I'll play this video just to kind of show you where I think one of the reasons why I think we might be getting that enhanced temperature gradient. Because that's the next natural question to ask, right? Is, well, where does that come from? You have this thermal discontinuity. What else could be going on? So as we approach the ice lens there, I'm going to pause it right when we get close. So we're just pushing through the snow grains. Just a bunch of x-rays. And right about, whoa. Okay, maybe we can do that again. Oh, just leave it right here. Okay, so what I want to point out is, first of all, these little striations you see in there, those are all the new ice crystals growing off the bottom side of the ice lens. The big globs are the snow grains. So there's a limited number of points of contact between those snow grains and that ice lens. So as heat is trying to make its way from warm to cold, it kind of comes to this roadblock, right, where there's only so many pathways that it can take. And that kind of slows everything down at that point, so you can kind of get that enhancement of the temperature gradient. And a similar thing actually happens above. But I think that's why we get more of a temperature gradient, or a larger temperature gradient, you might say, below than above. So something to think about, the way that the layers not just get put down and what they are, but also sort of how they stack up and how they connect to one another. I think could also be important in this process, and that's what I think we're looking at with the micro CT here. So you can read more about this if you want in a couple of academic papers, or you can pull up an old Avalanche review called "Leave Your Thermometer," an article called "Leave Your Thermometer at Home, but Don't Forget Your Loop," which is kind of my new mantra now, that I think we should all be spending more time in our snow pits, not so much looking at temperatures and temperature measurements, but the crystal types. What are they actually? I think being able to see a facet says so much more about what's going on than what the temperature gradient might lead you to believe one way or the other. And then don't forget that snow pit that you're digging, that time you're looking in your loop or measuring a temperature gradient, it's just a snapshot in time. Snowpack's dynamic, it's always changing one way or the other. And sometimes the instruments that we have to play with out in the field might not be telling us what we want to know. And it's good to be aware of that, and sort of cognizant of that as you go forth and dig more snow pits. So what we're doing in the lab right now is using a wind tunnel to build up what I consider the other end of the spectrum of this. So this was a snow-ice interface I was looking at, so very specific condition. And what we want to look at now is what about the opposite end of the spectrum, about subtle density changes. So you get a wind slab that gets put down one day, and a couple of days later another wind slab. There's always, that stratigraphy is now part of that snowpack, right? It's going to be there. So what's happening at that interface? Could there also be a stronger temperature gradient there? Those are sort of the questions I'm trying to tackle right now, and then hopefully we'll be able to fill in everything in between. I think that's all I'm going to go for right now. Happy to answer any of your questions and talk with you more later as well about ice-snow interfaces. Thank you.